Greetings all. Welcome again to the class. The way I want to start this particular class is to start in the most obvious way, and that is, let's start with a definition of just what the subject matter of this course is all about. I tend to start my calculus class with a similar kind of thing, and it's actually an interesting discussion to try to get an idea of what the students think. What is calculus? Well, in this particular case, this is a class in differential equations. I've mentioned before that it's already a calculus class, but why not start with what the heck is a differential equation? Or in this case, an ordinary differential equation. So I'll start with a bit of a more general thing, and that is a mathematical model and really, a mathematical model, I mentioned this in the welcome video before, a mathematical model really is nothing more than a function. A functional relationship between two measurable quantities, one of which you know something about, you have some control over, you know the values for. Sometimes that might be time, sometimes that might be position or some other quantity. And the other one, the dependent variable, is another measurable quantity that you're trying to learn something more about. Okay? And the study, the mathematical model, allows you to sort of analyze in that particular case. Now, what's interesting about mathematical models is that often the function is known. You may have some data, and you might fit a curve to that data. And now you have a continuous function which says something about, I don't know, the efficacy of a drug as a function of dosage, or as a function of time after injection in the body, something to that effect. And if you know the function, then you can look for its properties like, is there a largest efficacy? What are the bounds of the function? Does the function behave a certain way? And that's really, in some sense, where calculus comes in. But sometimes f of x is not known. But even in this case, if you have a mathematical model and you don't know the functional relationship between the two quantities you're studying, you still might have knowledge of some of its properties. Okay, for instance, you might know its derivatives. There might be relationships between those derivatives. And this, in essence, is what differential equations studies, this notion of a mathematical model where we actually don't know the function yet, and maybe sometimes we can find that function. Okay. So a couple of examples that we will talk about a little bit here are examples of this place where we might have a mathematical model, but we actually don't know the function yet. Maybe we can find it, but that takes some work. So here's the first one. Y prime equals k times y, where k is a real number. Okay? In essence, this is a mathematical model because it involves a functional relationship. In this case, we don't know, and maybe I'll write this as dy dt, so we can discuss it as y is a function of t. I don't know what that y is, but I do something about its derivative. I know that the derivative of a function is proportional to the function itself. Now, if k were 1, tell me, can you come up with a function whose derivative is precisely equal to the function itself? You've had calculus. You know that there are certain functions where if I take the derivative, I get exactly the function back. Y of t might be e to the t, and that's such a function that actually would be the mathematical model where you're given this partial information and you get to find it yourself. 3 times e to the t also works. The function 0 is a nice function, and that function works for this guy too, but this is an example of a differential equation, which we'll find in a second. This is an example of a mathematical model. Okay, that's one. 2, here's another one. F equals ma. If you've had a physics class, you might recognize this. This is actually Newton's second law of motion. And what it essentially says is the sum of the forces on an object, acting on an object, is proportional to the acceleration of that object. That's what the A means in this case. Now the A, remember, acceleration is the derivative with respect to time of velocity. Velocity, in turn, is the derivative with respect to time of position. And this becomes a mathematical model that measures the position of an object in some force field over time. And what you have here is that the total forces acting on an object are proportional to the second derivative of position with respect to time. This becomes a differential equation, which I'll define in a second, but that's another one. 3, the third one is f prime of x equals x minus 3e to the 2x. Okay. Tell me a function whose derivative is given by this expression in x, right? You might recognize that from Calc 1. Somewhere towards the end of the Calc 1 class, when you start looking at antiderivatives and differentiation, this guy looks a lot like if I just did this. And I said, calculate that integral. That's an indefinite integral. I'm looking for the antiderivative of f of x minus 3 times e to the 2x. And in essence, I'm asking the same question. Here's a function. There exists some function f of x whose derivative is x minus 3x 3e to the 2x. Tell me what the function is. And that function becomes our mathematical model. 4, the last one, d squared theta over dt squared plus g over L sine theta equals 0. You might recognize this if you've had a physics class that involved a bit of calculus. That's what we call the mathematical undamped pendulum. And really, in essence, what that guy measures is if we take a pendulum, a mass of a certain size, a ball of a certain size, of a certain mass, on the end of a rigid rod. We attach the rod to a fixed point here, and we can measure the position of that pendulum over time by a number of things, but this becomes the angular position of this guy, and really, in essence, they can take any position along that particular circle. Okay, so this is called a mathematical pendulum. So the position of that pendulum at any given time is the mathematical model. We don't know the position at any time, but we do know that it satisfies this. This guy is an example of this F equals ma in classical mechanics, and this one is actually pretty hard to find the position with respect to time for this particular pendulum. We'll see that later on, actually. So this comes up to a definition. And a definition is an ordinary differential equation is really nothing more. It's an equation involving an unknown function, y of x, and it may not be y of x, it could be something much more general than that, or any other variables, and some of its derivatives. Okay. So these become differential equations because the unknown function here is y as a function of t, and this is an equation between y and t and some of its derivative, some of the derivatives of y. This is, again, another kind. This, again, is an unknown function. I didn't call it y in this particular case, but it's f of x. And then this guy, theta of t. All these guys wind up being examples of differential equations. Now, I'll leave you with 2 notes. First of all, the notion of ordinary means that the unknown function is a function of one independent variable. Okay? There is such a thing as a partial differential equation, and that involves an equation involving an unknown function and some of its derivatives and some of its partial derivatives, where the function is usually a function of more than one independent variable. That's not the focus of this class. This class studies ordinary differential equations. That's one. And two, a lot of times the idea of solving this, finding the unknown function, finding an expression for the mathematical model, sometimes that's doable, sometimes that is not so easy. But often when we're given a differential equation, how we solve the differential equation is going to depend upon the structure of that differential equation, the properties of that differential equation. Sometimes those properties will lead to a relatively straightforward method for solution. Sometimes they won't. And really, like integration in calculus, sometimes it's actually impossible to find the unknown function, so we're left with some sort of analysis to say something about solutions, even if we can't find the unknown function. And this class is going to be based a lot on this notion of looking at the properties of differential equations in the hopes of maybe coming up with a solution or saying something meaningful about the differential equation. So just to leave you with the first bit of information which is going to be useful for us, and that is, notice that in this first guy here, the unknown function is y. There's a relationship between the derivative of y and y itself, and there are no other derivatives. In other words, the highest order derivative in this differential equation is 1, the first derivative. Notice at the last guy, that's not the case. I have the 0th derivative here and the second derivative of theta with respect to time. Here, there is no first derivative, but the highest order derivative on this guy, this one right here, is 2. This guy, again, is 1 because I have an unknown function f of x, and then the first derivative of f of x is in this equation, no others. This guy, the acceleration, remember, is the second derivative of position. So really, this guy, the highest derivative in this equation is the second derivative. Okay. The order of a differential equation is one of the properties of a differential equation. The order of a differential equation is just the order of the highest derivative in that equation. So this guy here, maybe I'll switch color. This guy here is first order, as is this one. This guy here is a second order differential equation. And then this guy also, even though it doesn't even look like a differential equation, if we interpret A as acceleration, it's the second derivative of position, this guy is also a second order differential equation. Often this is one of the relatively straightforward things to detect in a differential equation for the most part. And it gives us a lot of information about how to solve differential equations because first order and second order, there are third order equations, fourth. There exists, we can write out a 17th order differential equation, and the methods that we might use to analyze and solve will say something about that order. So that'll be a very important aspect. So with that, we're going to leave this for now. We'll come back again and talk a little bit more about the properties of an ODE before we get into some specific examples. But for right now, we can just leave it there. And thank you for listening, and we will talk again very, very soon.